it would be good to have the rest of the people who are at the lab here. We are very, very honored to have with us Algo. Algo is a truly leading person in the field of economics and econometrics. He has been editor in the Journal of Econometrics, which is one of the most prestigious journals in the field. And we are blessed by the fact that he got interested in natural resources. He got interested in understanding how natural resources move in time and how the dynamics of time series can give us information about what is changing in nature. So before us, we have one of the greatest econometricians looking into things that are bringing, that at least try to understand the dynamics of natural resources, biodiversity, water, climate, and the variables that define climate. So he studied in Delhi, then at LSE. He's now a professor, a retiring professor, which is good at some point, from the University of Maryland. And I will not waste any more time. I will give the floor to Alok, and let's see what interesting information we can grasp for this. Thank you for being here.
Thank you for that kind introduction, Phoebe. And I apologize for not linking with you earlier, but I've been working on my own and looking at all these complicated in situ and remote sensing data sets. Climate is a very broad field, and I've been teaching PhD students at Maryland on from the civil and environmental engineering because they don't take any statistical courses, and so the professor sent them to me. And I think that there are a vast amount of data available now, but there are all kinds of problems with remote sensing data which are not recognized, and so I've tried to sort some of them out here in this paper. It was written at the invitation of, this is a paper on diet quality, and I have an earlier paper in the World Bank Research Observer, but I think the issue really is now that we are depleting groundwater very rapidly, and so how should we plant crops in the wake of climate change? What is happening to groundwater? And, glaciers are, appellations from glaciers are feeding these rivers, and what is happening to glaciers? It depends on, there's all kinds of methodological issues involved, but unfortunately, climate scientists are not really interested in these details as much, and I'm hoping that someone like Phoebe would use her influence to change their thinking. So let me just try to rush through this because it's a complicated paper, and I'll pause every 5 minutes to see if you have a question or something, but otherwise I'll try to finish within the 45-minute time frame. So we all know, actually it was Arrhenius in Sweden in 1896 who recognized that, climate was going to, ambient temperatures were going to increase as a result of higher carbon dioxide concentrations. And IPCC has all these reports. And I think my paper in the Journal of Royal Statistical Society Series A actually provides all kinds of evidence for Northern Hemisphere, Southern Hemisphere, different seasons, and so on. Now, these issues are really not addressed by IPCC, and I don't know why. But, it's true that the summers are getting hotter and longer, winters are milder, and so on. And, with the tilt of the Earth, it's not appropriate to have a single temperature anomaly. If you want to, which is a deviation from some time mean, if you really want to understand climate, you really want to see what's happening in the Northern Hemisphere, what's happening in the Southern Hemisphere, and they're linked by these ocean currents. So I have a paper in the Royal Statistical Society and then in the Journal of Marine Science and Engineering, pointing out some of these things. Now, the United Nations has come up with these 17 Sustainable Development Goals, And the goal number 2 is about improving diet quality, eliminating hunger, and promoting sustainable agriculture. Now, how do you actually go around doing that? You need very elaborate analyses of longitudinal or panel data and see what are the mechanisms and how we can understand them. How should we formulate evidence-based policies? Now, for example, agricultural production entails the use of surface and groundwater. And, in countries like India, in the semi-arid regions, because of electricity subsidies, they're producing a lot of rice because rice is a lucrative export. But the fact is that they're depleting a lot of groundwater. But to measure the groundwater depletion is not that straightforward. I'll just come to it in a minute. But, for example, okay, so let me just go back and say that, rice is not a very efficient crop from the viewpoint of transpiration efficiency. It takes a lot more water. But rice is actually a very good staple. You can mix it with pulses or lentils, vegetables, meat to improve diet quality. That's what I had argued in my paper in the World Bank Research Observer. But the problem is that groundwater is being depleted at a very fast rate. And, these rates may not be sustainable. Now, there are these GRACE satellites, and I'll come to that in a minute, but their resolution is very poor. These are remote sensing satellites, 2 of them. And the resolution rates area is about 200,000 square kilometers, which is a lot of area. And in fact, in a paper in the Economics and Human Biology in 2019, I tried to show that these data are not useful for making climate agricultural decisions for planting crops and so on. By contrast, India has this, Central Groundwater Board has these 36,000 wells in which they're supposed to measure the well depth every 3 months, even though they don't actually do it most of the time, but at least once a year or something like that. And I'm going to analyze some of those data and try to show you that the well depths in India are increasing as a result of excessive groundwater, as a result of excessive production of rice. So I'll come to that in a minute. But so again, glaciers are very important. They are so-called water towers. And, they store fresh water, but the glaciers, especially in the Himalayas, are starting to thin, and glaciers worldwide are thinning, but not at the rate at which these people from, Huguenet et al. And so on, and they're publishing all these papers in Science and Nature without actually examining the stochastic properties of their time series. Yeah. And if they were to do that, they will realize that they've made a bit of an error in processing these remote sensing signals. Glaciers are not disappearing at these rapid rates. I'll come to that. That's one of the main points. Now, by contrast, so there is this person called Jasenko, and he's put together in Science, a long article about groundwater depths all over the world. But, we need to observe them longitudinally. We need to have time series so that farmers can decide what to plant and what not to plant. So glacier thickness is also measured in the GLACIDA database by drilling holes into the glacier and trying to see what the glacier thickness is. The problem is that they measure the glacier thickness at different points of the glaciers, but they do not repeat the observations over time on the same glacier. So you don't know how the glacier is actually thinning. There may be some sort of exceptions in the Svalbard region where some glaciers have multiple observations, but I'll come to that in a minute.
Have reason to believe that the neighboring glaciers would have significant difference, statistical significance?
No, but there are 4,351 glaciers in this database. And the problem is that they're measuring at different points of glaciers. They may have 1,000 observations on the same glacier in the same time point. So I will explain to you that how do I actually construct a longitudinal series. So the remote sensing data that Huguenet et al. Have computed, they're very comprehensive in the sense that you've got 20 years of data on changes in glacier thicknesses. The problem is that they've been generated by these algorithms. And so in my view, as I will show you, I don't think they're reliable. Yet Science has just published an article claiming that, how temperatures are affecting glacier thicknesses. But these data are really, it was Norbert Wiener, the famous mathematician who wrote a book in 1949. And, he made this point that all these kind of filters are going to contaminate the time series properties of these of these series. So I'll come back to that in a minute, but it was Wiener's book that is very inspirational. And, he made this point, but none of these climate scientists actually have read that book. So I'll explain to you how they actually compute some of these things. So this is my model in the Royal Statistical Society Series A 2022. So you've got all these industrial and agricultural activities feeding into CO2, carbon, methane, and nitrous oxide emissions. They in turn increase the ambient temperatures. And once the ambient temperatures started to go up, that increases, that can reduce glacier thicknesses. And all these emissions are increasing ocean acidification and deoxygenation. And as a result, sea ice thickness is also going down, and sea ice is connected to polar ice. So polar ice thickness is going down, and that's how, the glacier thickness also is going down as a result of higher temperatures. So I know IPCC has very similar things, but, the problem is that they are relying too much on mathematical models. And, they just think if you can control or you can keep the temperatures from going up more than 1.5 degrees centigrade, it's actually going to resolve the problems. But the problem is, as I tried to point out in a letter in eScience, that many of these things cannot be dealt with social costs of carbon, for example, because, it's very hard to measure carbon in the oceans. Most of the carbon dioxide is actually absorbed by the oceans. But if you want to know how much carbon there is in the oceans, it's very difficult because it depends on the depth. At lower depths, there's less carbon. At upper depths, at the surface, there is more. So
we don't have access in the very deep ocean.
Well, we have access so it goes down to about 50 meters in the World Ocean Database. And so they take the in situ measurements and they measure the dissolved oxygen levels, the pH levels, and temperatures and so on. But there are only 400,000, the oceans are vast, the total. So they published some articles in Nature, which they had to withdraw, from the Scripps Institution. And the reason is that this is the only database that is available in situ. And when I wrote to these people, they said, "Oh, we don't know much about this data set." But that's like the economists saying we've never heard of the World Development Indicators. It's all a bit strange because there's a tendency of relying too much on mathematical models to predict what is going to happen and not actually looking at what the data is saying. So Ralph at Scripps Institute, they had to actually withdraw their paper because they were making these claims that oceans are warming at certain rates, which they are not, because the World Ocean Database actually indicates otherwise. So there are all these, I'll try to cover them, but given 45 minutes, it's a very... So what I've got here is that I'm trying to show that if you looked at the proportion of rice produced in relation to rice, maize, sorghum, pearl millet, and, is it the case India is producing a lot more rice, and that is the reason why groundwater is depleting. So I'm going to show you some evidence in a minute. Now, I'm also going to show you the relationships between glacier thicknesses from in situ data versus remote sensing data. And the picture is very, very different. And, people have not recognized this. These scientists are writing papers in Nature and Science with high impact factors. But what they're saying is a bit misleading because there is really no evidence that the glaciers are disappearing at an exponential rate, practically. That's what is implied by some of these data sets. Now, of course, from a policy point of view, we don't want countries like India to subsidize electricity, so the farmers then pump out a lot of groundwater in semi-arid regions and so on, and produce these lucrative crops like rice and so on. So what I've got here, and I'll leave enough time for discussion because I will brush through most of these things. So you can get some data from the FAO stat database, but they don't actually have, they have data for whole of India, for example. They don't have data on groundwater depletion. And so what I've done is to use the ICRISAT data on 310 districts in India on the production of rice, wheat, sorghum, maize, and pearl millet during 2000 to 2017, temperatures on ambient temperatures and well depths, Now, these well depths are very well measured in the sense that if you compare them with GRACE satellites, the GRACE satellites are really completely off because these are they're not really measuring aquifer thickness. What they're really measuring is if the weight of the construction and other things increases, the speed of the first satellite increases slightly, and based on that, they're kind of projecting how much aquifer thickness may have gone up. So again, you have very systematic, a lot of data from GRACE satellites, but in my opinion, they're not very useful. And we also have data from milk production at the state level. And milk is an essential food for especially children, their heights and so on. I have papers in Journal of Nutrition, which actually Hilton Birol had kind of forced me to write. And, it was a very difficult paper to publish, but it did get published in Journal of Nutrition. And it makes the case that, that protein and calcium intakes are very important for the heights and for growth of Filipino children and so on. And so in order to minimize this kind of variation in the data, there are 6 3-yearly averages for 2001, 4, 7, 10, 13, and 16 that are analyzed. Now, the glaciers, there's been no study whatsoever to compare glacier thicknesses in situ data versus remote sensing. Now, the in situ data are in this GLACIDA database, and there are over 3 million observations there. There are 4,351 glaciers, but there are all kinds of different points on the glaciers. So these data were analyzed now to see what is happening over time. We are not observing the same glaciers over time. So what you can do is to construct some sort of grids. Now, you know that those of you who are mathematicians and, you studied Riemann geometry, these grids are not the same area. A 1 degree by 1 degree grid at equator is 5,000 square kilometers, but at the North Pole, it could be just a few hundred. So, these issues have not been addressed either. But anyway, I'm trying to just simplify things and construct these 1 degree by 1 degree grids and see what is happening to these glaciers over time using in situ data, not the remote sensing. And so they are actually panel data, if you like, for 180 grids with 2 observations, but these are 6 yearly averages between 2000 to 2011 and 2012 to 2017. So this gives you a kind of a benchmark, how to compare the remote sensing data with the in situ data, because everybody right now in science, nature, they're all focused on remote sensing data. And remote sensing data have all kinds of assumptions that they're based on. So that's the remote sensing data. They're based on these so-called digital elevation models. And basically, when the lasers and other things are pointing at the glaciers, how much time does it take for the lasers to be reflected? Based on that, you're trying to assess what is the change in heights or mass or volume in these glaciers of 0.5 by 0.5 degree grids. Now, again, most of these glaciers are in the northern hemisphere are at very, and even in the southern hemisphere, they are focused on high latitudes in absolute terms. And so, these are quite reasonable things to do. But the problem is that you're applying all these algorithms, such as these stereoscopic remote sensing signals, and there is all kinds of heteroscedasticity in these grids because the terrain slopes are not really constant. Sometimes they're very, very deep, sometimes they're very flat, and so on. So you're adjusting for all kinds of things. And so what is the net effect of this adjustment? Nobody's ever examined it, and I'm producing some results here, which I'll show you in a minute. And so basically, I'm looking at quarterly data for something like 3,989 grids in the northern hemisphere, and these cover the Himalayan region as well. Now, the critical thing here is, what are the stochastic properties of these time series? I mean, are they really as reliable as, for example, the in situ data? And I'm going to argue they're not. So basically, then let me try to cut down the things and focus more on the results. So basically, there is a model for well depths. This is climate and agriculture. The well depth is a function, well, what's happening over time. and so on. And then things like latitude, longitude, rainfall, maximum temperatures. And the point is that, is it the case that the grains produced in the previous period are increasing the well depths, and especially of rice production? And this is the dynamic model. So the well depth in the current period depends on well depth in the previous period. And these are random effects models. You could have fixed effects models, but they would be very inefficient, and you can't really have lag dependent variables when you have small number of time observations. And then there are these data set, these models for glacier thickness using the Glatida in situ database. And then there are these models for remote sensing changes in glacier heights. And we can, these are as comprehensive as we can go at empirically, because we are not really making any assumptions. I'm not making an assumption that if carbon dioxide levels go up by a certain amount, glacier thicknesses will be affected or temperatures will be. I'm actually looking at what the data say and trying to reason things out. Do you have any questions I can take a little pause, and otherwise I'll continue and try to finish up.
I don't think there are non-linear effects there. For example, squares and cubes of variable.
Yeah, they're mainly squares because it is, the cubes are, we don't really have enough observations to measure cubic effects and higher order.
I think that they be.
Absolutely, yeah. So these are the sort of models, and let me just try to present the results, skip the econometric part. Now, one of the ways you could measure, you could assess whether these remote sensing data are reliable or not is by looking at their stochastic properties. And if you look at their stochastic properties, you see that something is going wrong. They're becoming very, very, it seems that the glacier thicknesses are really declining at very rapid rate. So I had proposed some tests in my thesis many years ago on looking at non-stationary processes, and I'll just show you some of these things a bit later on. But now let's just keep things simple. So here, this is in India, the milk production is really going up, and you've got rice production, which is increased slightly, but water efficient crops like sorghum, they're not very appealing to people as they become more affluent, and yet India should be growing more of sorghum and so on because they're water efficient. So I'll talk about this in a minute, but you can see that the well depths are increasing in India, and rice production is also increasing, and most of these grains are going up slightly over time. Now, basically, if you do a very simple paired t-test, you find that there's a statistically significant increase in rice production, increase in well depths, and so on. And milk production certainly has increased quite dramatically, even though this is not at the district level, it's the data for 14 states. Now, I'm going to skip this for, this basically tells you what are the effects of rice production on well depths and so on. And I'm not going to focus on this table, but on the next table. And here you can see that, we're explaining the well depths. And this is the logistic transformation of the rice produced, and it's actually positively associated with well depth, and so is its square. Now, in the previous table, actually, if you looked at the square, they have the level as a negative, the square as a positive sign, level as a negative, positive sign, and so on. But when we look at the proportion of rice produced, we see that if you produce more rice in relation to the other grains, it's actually going to be associated positively, not only with well depths, but even the square terms. So well depths are going to keep increasing at a faster rate if you produce more and more rice. So that's what these results in general show. Now, there are all kinds of complications, like, what is some of these variables on the right-hand side are correlated with the error terms, the endogenous variables, but you can estimate these models using maximum likelihood methods and take care of many of these problems. But the basic result is that as you produce the higher and higher proportion of rice, it is going to lead to greater and greater groundwater depletion. So these non-linearities, as Phoebe was saying, are actually quite important because it's only after you go over a certain level that, you shouldn't be producing more rice than a certain amount. And when you do that, you actually see that the well depths are positively associated. And in general, milk also requires a lot more water. So if you want to improve diet quality in countries like India, you need to produce, more milk, unless you can think of some substitutes. Now, there are many substitutes. You can produce gruels based on, like Nevin Scrimshaw did in the 1960s in Guatemala. You can take cotton seeds, you can produce gruels, but the fact is, as incomes go up, people nourish themselves better. They want to provide milk for their children, but milk also requires more groundwater. So that's one of the big issues, and whether we should think about, from an economic point of view, whether we should increase the milk consumption, or should we give supplements to children based on water efficient crops like cotton, for example, and sorghum, and so on. So, okay, so that's the agricultural part of the paper, and it's basically saying that there isn't very much emphasis on transpiration efficiency of crops, but there should be a lot more, because even in European countries, certain countries, you want to avoid wasting water. So, for example, if you go to Egypt along the Nile, it is horrifying to see that the amount of sugarcane they're producing, because their sugarcane is a very water inefficient crop, and it's not good to consume too many sweets anyway. But if you produce if you produce the excess amount of sugarcane, you're really reducing the levels of Nile. And if you take a boat on the Nile, you can see that on either side, the main crop that is being produced is sugarcane. Now, Food and Agriculture Organization had some early reports on these kind of issues, but they are really not being mentioned very much. And climate and agriculture are so closely interlinked, especially for economic development. There is no way we can think of economic development in the wake of climate change, higher ambient temperatures, what is happening to groundwater availability, and we really cannot be depleting so much groundwater. So let me just then get to these glaciers, and if I'll be happy to answer any questions that you have. But here, if you take these are the in situ data on glacier thickness. They're very reliable. You are actually drilling a hole and measuring how thick the glacier is. There is no assumption being made of any kind. So if you look at average glacier thickness, there are only 2 time points because of constructing these variables. But you can see that, if you put a dummy variable, for example, it doesn't really show that the glaciers are thinning very rapidly. They're thinning to some extent, but not very rapidly. Now, again, if you construct these 1 degree by 1 degree grids, you see that the average glacier thickness, again, of course, at higher latitudes, this is all in the northern hemisphere. At higher latitudes, these glacier thicknesses are higher, and elevation, of course, is positively associated as well. But, it's not clear what the trend is. And if this is a data with 2 time observations, a panel data analysis, and again, here, the time indicator is not statistically significant. So if you look at these, now there is a drawback in these in situ data. The drawback is you're not seeing the same glacier over time, because there are just so many of these glaciers. In the Svalbard region, there are a lot more glaciers. Some of them are observed multiple times, but it's a very small sample. So on the one hand, you have this problem. You don't know over time, maybe they included different glaciers in different time periods. You really can't tell whether or not glaciers are thinning or they're not thinning. Now, having said that, let's go and take a look.
Isn't there a theory in marine science that identifies homogeneity, let's say, cover area of homogeneity in the properties of the glaciers? That could solve your problem slightly.
Actually,
the no repeatedness of the same data point. if you have a theory that says that if they are neighboring each other, they are unlikely to be very different.
That's true, but most of these glaciers are not. So, for example, in the Himalayas, there are 15,000 glaciers.
Yeah.
In the whole world, there are close to 120,000 glaciers or 150. And, geographically, even if they are close, you could use data on another glacier, but we've got only 4,000 glaciers in our sample. So maybe from 200,000, we have data only on 4,000 glaciers. So it's very difficult to construct what is going on over time. So the point I'm just trying to make is that instead of drilling so many holes in the same glacier, if they were to just come back and drill holes around the same spot every year, then they would know what is happening to the glacier.
Yeah.
So that's the point. Now, what you're referring to is the so-called physics of glaciers.
Yeah.
They are looking, I've been reading all these books and,
Yeah, I know, I'm trying.
it doesn't solve the problem. That's the problem, because all they're doing is that if you look at the slope of the glacier, you can say, well, what are the chances of ablation? You can look at, very simple, something like the hypotenuse r cos theta and see what the mass of the glaciers may be and so on. But, the problems are so complicated because you really have no idea. Right now we are seeing all these glaciers bursting in some places, and it is eventually going to be the case in the next 50 years or so. There'll be very few glaciers left at high altitudes. But if you believe the next set of data that I'm actually presenting, many of these glaciers are going to disappear very soon, within the next 10 years, which I don't think is the case. But, it is true. I tried that, what your suggestion is for Svalbard. Because in Svalbard, the region is low,
Yeah.
it's quite north, the grid is very small, and these longitudes are meeting at the North Pole, and so it is not that difficult, and you could do something. I haven't done a detailed analysis, but I did look at some of the data from Svalbard, but they also show very slight reduction in glacier mass, so glacier
This
thickness.
is good news, actually. That it doesn't matter that it doesn't fit the current state of discussions. It's good news that it's going slower.
Yeah, it is, but science and nature are publishing these papers, and I'll just show you that if you look here, these are the remote sensing data from Houdinot et al. And I'm not a believer in doing aggregate analyses.
No.
And you can see Q1, Q2, Q3, Q4. Because of the tilt of the earth, we have all these seasonal factors. It's very different, the properties of the glaciers in the winter quarters versus summer quarters and so on. But you can see if you put in these time dummy variables, they all have very large negative coefficients. And in fact, I'm just going to show you these last two lines, they mean something else. So if you believe Houdinot et al. Paper and say that glaciers are really thinning at a very rapid rate, you can see that it's really not plausible. These are the changes in glacier heights. So it's not only the glacier heights, it's actually the changes. The changes are going up over time. Glaciers are thinning like anything. So for example, instead of these dummy variables, you just put in a trend variable and a trend square. Trend variable has a negative coefficient, trend square also has a negative coefficient. So not only glaciers are thinning, but the rate of thinning is actually increasing over time. Now that is very implausible. What is likely is that the glaciers are thinning, but at a nonlinear rate, in the sense that the rate of change is smaller and they're not increasing, they're not thinning at an increasing rate. So if that was the case, we will have no glaciers left within 20 years. I've not made the computation to see how many years it would take for all glaciers to disappear. But you can see that we have data here on something like 3,900 grades. And based on that, whether you are in Q1, 2, 3, 4 in the Northern Hemisphere, these changes in glacier high mass, glacier volume are actually increasing over time. It's really not plausible. And the reason is that when you've got all these signals, you've got all these rough terrain and so on, the light is not reflected in different ways because of different reasons. You start adjusting everything. And so when you start adjusting everything, you make the series look more like what you think it should be looking like. So inadvertently, I'm not saying they're doing this deliberately. The problem is
Who is adjusting?
these are the people, this is a team of glaciologists, and this is,
Have you talked to the British Antarctica Survey?
no,
I would put you in contact with them.
that would be
Very interested. They are actually located in Cambridge.
oh, yeah.
So next time you are in Europe, I arrange you to give a seminar to them.
Definitely.
Because these are the people that collect in situ data, and they are paranoid about the situ data as vis-a-vis satellite data. So you might find
Oh, I'd be
there.
very happy
Yeah.
to be introduced. And, I mean, this is a very important issue.
So
And
how do they adjust? They adjust how they.
they fit in some trends, and they say, okay, this is a trend, but the coefficients of the trend are not linear, they're non-linear, and they depend on the grade level, they depend on the slope terrain and so on. And so by the end of it, they process the data so much that it actually looks like a very strongly
But if
trending.
you include the trend, you need to convey some understanding of why you
Yeah.
put the trend in, right?
But this is the point I'm trying to make. They don't take courses in
The
statistical
trend
methods.
says something.
Yes, I mean, you can see here, the trend is negative and it's increasing over time. So mass and volume are going down, the changes. So this is already a first, it's a second order sort of a thing. It's not even a first order time series. So it's a second order, and there the changes are taking place at a very rapid rate, which is not feasible, which is not plausible.
And you're saying that this is because they not manipulate.
They process.
They process the data through these trends,
Right.
which is making the, okay, what,
They're making the time series highly non-stationary.
yeah, they are
Because
making,
they
this
just-
is exactly what they are doing. They are making the time series highly non-stationary. But what is the narrative behind inputting this trend in
Because
that they give?
they're saying we're dealing with almost 1 billion observations and so on. And when we look at them, we see that there are these heteroscedasticities and their trends, and these coefficients are not constant over time. So we fit in a polynomial of some kind, and then we adjust the data, and then we produce this figure. So for example, one of the peculiar thing is they don't have an initial observation. They say we cannot measure the change, we can only measure change in glacier heights, mass, volume.
Yeah.
We cannot measure the level of height, of volume or thickness and so on. So, okay, I understand that too. But the problem is that the way you're processing these data, you are inducing all this non-stationarity in the time series. And so, there are very few people who understand that, I'm afraid. But I've been trying to convince them that, we've got a serious problem. You cannot make these assumptions. In fact, if you actually look at some of these statistics, you see that not only they've induced unit roots into the different time series, but there are also these grid-specific trends. So everything is really, it's as if everything was exploding. I mean, glaciers are melting, and some are exploding, maybe 1 out of 200,000 or 5 out of 200,000. All this skiing business is going to become very difficult because, there are different levels of ice thickness, and they're all melting. But they're not melting at these high rates as what they're claiming. So let me just give you a little summary, and then I'll stop here because I know Phoebe has another. I can only do one thing at a time, but he's got. I can't do more than one thing. So let me just give you a summary, and so we saw that we have quite a few different policy insights. The FAO stat database, if you try to analyze them, they're very difficult to manipulate, and they're very large. For countries like India, there's just one observation. But the district level data from India are quite reliable, and they showed increases in well depths. Now, milk production was associated with higher well depths as well, but in a non-linear way. But it's not that it's increasing with milk production. And Harvest Plus, which was actually founded based on a paper that I wrote with Howdy Boose and Nevin Scrimshaw, And, they've been promoting these biofortified crops, which are high in such as iron-dense beans, iron-dense rice, or orange flesh, sweet potato, and so on. So basically then, in the future, if the world is running out of groundwater, surface water, we are going to have to rely on these biofortified crops and, create some sort of rules, for example, with cotton seeds and sorghum and so on, to increase the protein intakes of children. And countries need to really monitor the well depths. And, it's not enough to have these gray satellites, because these gray satellites are really very approximate. I mean, 200,000 square kilometers is a lot of area. And there too, you're not really measuring the aquifer thickness. If you've got construction going on, it's actually increasing the weight, so that when the first satellite comes, it speeds up a bit. And these people are assuming this is due to increasing aquifer thickness, which is not the case. So, we have got all kinds of problems in the scientific literature, partly because they're not taught all these statistical methods. Whenever you produce a time series, you need to assess what the stochastic properties are. If they're implausible, then your series is not plausible either. So that's the point I've been trying to make. And that's why they don't even consider my papers. They just turn them, say, this will not interest the broader community. The problem is they have to address all these issues. And, I'm just trying to make these points. Now, in real time, we need to measure these well.
The problem is that econometricians do not care about the interdisciplinary work. That's why. So they cannot find the relevant reviewers for them.
Well, that's also true, but it's also true that the scientific journals are, they're used to their models.
Yeah, they don't know.
Yeah, they just like figures which are black, blue, red, green, and you press a button, they say create a video. If you want to get a paper in science, you press a button and suddenly things light up. What is it all about? I have no idea. So certainly groundwater should be recharged. In fact, if you go back to Indus Valley civilization, in India was recharging its groundwater more than 9,000 years ago. But now, there are very few states where they've come up, like in Maharashtra, they're using canals to recharge these wells. And as the glaciers disappear, there's India, China, Pakistan, and so on, we are going to have very serious water problems and water shortages. So we need to store this water underground. We need to avoid wasting it. We want to grow crops based on their transpiration efficiency. Now, we saw that it's important to monitor glacier thickness using in situ data on the same glaciers. The GLACIDA database showed very insignificant sort of results, but by contrast, the remote sensing data showed rapid changes. And I think that is partly or mainly because of the filters that they're applying to process these remote sensing signals. Now, certainly lower carbon dioxide concentrations will help reduce ambient temperatures. Now, there's also this other fad about aerosols, that, if a volcano erupts, it is dark and that earth cools down a little bit. But that's a very temporary effect. The problem is that if we have all this pollution of sulfur and carbon in the atmosphere, and this black carbon falls on glaciers, it actually increases the melting of glaciers and sulfur as well. So there are all these fads. I don't know, I thought we economists are the best at generating fads, but it's actually quite bad in the scientific literature as well. And, if you've got sulfur falling on glaciers, they're going to start melting. There's no way aerosols can actually protect us. If you're saying higher pollution is going to cool the earth down, you have absolutely no idea what you're saying. It may be true for a month, 2 months, 6 months, maybe even a year, but eventually it is not going to be the case. So essentially, in countries that are depleting groundwater, we need to cultivate these biofortified crops, for example, from Harvest Plus, fruits and vegetables. Fisheries could make up some supply of absorbable nutrients like protein and so on. And so it's very easy to talk about sustainable development goals. But if you take sustainable development goal number 2 and how to achieve it, you see you need a whole load of data sets. You need all kinds of complicated analysis. The scientific literature may or may not point you in the right direction.
For any of the 17.
That's right. And I had sort of mentioned this problem that, there's the interdependence between goals.
Excellent.
So, for example, in Tanzania in the early 2000s, they abolished tuition fee for primary education. The enrollment doubled. But what happens by fourth grade? Fourth grade, many of the children drop out because they're asked to do housework and so on. We're back to square one. So, countries like China, Japan, South Korea, by reducing fertility rates, educating their children, they've created this whole skilled labor force. By contrast, if you look at sub-Saharan Africa, in countries like Ethiopia, for example, if you go to Addis Ababa, the total fertility rate, which is the number of children per woman, is less than replacement rate. It's about 1.8. You go 10 kilometers out and it is 5 plus. So clearly, fertility rates are very important. And the point I was trying to make about sustainable development goals, there should have been a much greater emphasis on population growth and so on, providing contraception because most parents want to limit their family size. But even in countries like India, if you go to the rural areas, for example, in the northern states, you still have total fertility rate above 4 in many of these rural areas. So the point I'm trying to make here is that you've got 3 billion people surviving on water from the Himalaya region, and now these 15,000 glaciers will start to thin and melt. Eventually, they may disappear. And so we've got some really severe crisis coming. But
not at the rate.
Not at the rate of the remote sensing data, I say.
Let's focus on that in order to synchronize this supposed implementation of the SDGs at that rate, because the rate they are proposing in Science and Nature is impossible to handle.
No.
So it's like saying, I cannot do anything.
No.
Here you're saying maybe we can do something with the technological advance.
Also, we could try to reduce pollution in these areas. So, for example, India is building all kinds of things. China is building these dams and so on. And, this is very mobile region. The ground is very soft. And, if you have higher pollution, because of this, there's a guy called James Hansen. He promoted this idea that if you have aerosols, it cools the earth down. Now, it may cool if you have a volcanic eruption, there's no sun.
Yeah, but it destroys the resilience of the water system.
Exactly, and it's falling on the sun. It increases the microbial activity in the glaciers and so on. They start to melt and they are not reflecting the sunlight back. So the whole place starts to warm up. So we've got all these paradigms, and I don't know how they come up with these paradigms, but it's so I think that this is the critical thing. So I'll just stop here if you have any. Yeah, that's right.
I would like to ask Ivo's opinion, because he's a specialist in spatial satellite data and land uses. So how do you see all these proposing ability of satellites to get the accurate changes in the aquifers?
Quite interesting. Actually, here there are two basic questions. How to do by satellite data, groundwater depletion and glaciers. In fact, there are two main methods for monitoring groundwater depletion. Either you use GRACE, which is a gravimetric satellite, or SAR, synthetic aperture radar. They both measure the same thing, but by different ways. GRACE uses changes in the Earth's gravitational field. SAR uses simply records the changes, the deformations in the aggregate due to groundwater depletion. So both ways are indirect.
The deformation in the actual aquifer.
No.
The deformation.
The surface of the Earth.
Okay.
While GRACE uses records changes in the gravitational field due to groundwater depletion.
Okay.
But GRACE is not claiming that it is only groundwater. It could be construction, for example. So long the mass increases, the velocity of the satellite, the first satellite will increase, and then the second satellite will catch up, and then it'll be back to the.
Now, if you go to glaciers, you don't normally use GRACE, but you can use infrared, visible, shortwave infrared, various other satellite data. In any case, what is interesting, I think, if you want to measure or to monitor both, is use let's say, because that applies to both cases, if you're interested in both cases.
SA, this is the,
Sentinel-1, exactly.
but are the data actually available over time from these?
Yes,
Oh, if you could just send me a link, I can
sure.
try to.
Let's try to analyze that as well, and if we can get the same,
Yeah,
the same change rates,
Right,
then
right.
we can have a story there.
but is it available at what grade level? Is it 0.5 by 0.5 or? I mean, many of them are actually available at, I mean, for example, sea ice is available at 0.01 by.
Sentinel, and you can use Sentinel-1 data as a SAR method for both glaciers and groundwater.
No, so I've done the sea ice concentration. Actually, it's sea ice concentration and not sea ice thickness, which is again satellite remote sensing data. But there, the data are actually available at 0.01 degree by 0.1 degree grades. So we've got, I think, 648 million.
One is sufficient.
Yeah, but
Because 0.5 is too large.
no, but I'm using 1 degree by 1 degree because there's no other way out. But then, as I explained, that if you look at the higher latitudes, then 1 degree by 1 degree is not such a large area compared to the equator.
And you could also try INSAR, interferometric synthetic aperture radar satellite.
Actually, the Huguenot et al. Data takes data from all kinds of sources and then creates this sort of a merged type of a database.
Okay.
So that's
you're working on the merged data.
yes, that's right. That's what they produced. But there's someone called Daniel Ferinotti. I think you must know him. He's in glaciology in Switzerland. And he was responsible also for the in situ data set. But, nobody, I mean, the in situ data, you can see that there are no dramatic problems of any kind. But the remote sensing, you can see that, they've just been so heavily processed that it can't be true that this was the original.
I understand the point. I do understand this point, but we need to look into I mean, if you can download some of the data in the same areas
Right.
of the ones that you're looking at.
Yeah, you could do it for the northern hemisphere.
Yeah.
At whatever degree grade you produce. If it is 0.5 by 0.5, that's what I've been using, or 0.1 by 0.1. I can just estimate these models. It'll just increase the, we don't have any space constraints anymore on these computers, on the Unix platform and so on. So I can just use FTP if anybody sets up a site to download the data. But then it requires a lot of processing, and I can still do that.
That's some about the area you want to point to us.
Yeah.
I don't know what area you have.
I mean, one of the problems in the scientific field is that what happens is they use this format called, it's this, what they do, it's a very portable format, but every year they put the data onto the website. So for example, if you look at Copernicus website, and every year they keep putting the data and they're repeating a lot of the information, but nobody's ever looking at it, what is happening over time. And you can't merge the data easily because it's full of numbers and letters and words and explanation. And so it took a long time for a student of mine. So it's the net CDF format. That is the main format you people in climate use. And it's very difficult to open them in Fortran, which is what the language I write in, but it can be opened in Python and so on. But the problem is that every data file is so large and it's only for 1 year. And then, for the next year, you've got to remove the variables and wordings and so on, and then you have to merge them. So I was very lucky to have a PhD student who learned how to handle the net CDF files, and he created these databases. And then once he's got it in an ASCII format, I can write any Fortran program and, process them. So it's been a big sort of exercise, but I think the issue is that, somebody has to speak point out these problems. I mean, we can't just go on assuming.
The econometric problems behind all of this, would you make available the data that you're creating?
Oh, yes, yes. Whatever you want, I've been sending to people in India because, you know, Indian government has got this idea, clever, why don't we make some money out of this? And, you know, I mean, more research there is, the better it is for the economy. That's how the funds are, you know, flowing and so on. So I've got data on all these glacier thicknesses. I've got the Huguenot data he actually sent me. But, you know, it's at 0.5, 0.25, oh no, 0.5, 1 degree and 5 degree grades. So that, you know, he sent me and I'm happy to share. Glathida database, I processed, I put together these data, these grades. These are not very large data sets. But Huguenot data set is large, but not that large.
Okay, this would be, yes, please.
Yeah, okay, just a question. Okay, you're right about the errors of the remote sensing data because of all these corrections, the spacity, and all that kind of algorithms that try to fix the signal. There is also, this is the limitation of the remote sensing data. There is another limitation which has to do with the in-situ data, which has to do with their density. And the one degree, what was it, 1 degree? That you said? Okay. So you have maybe some averages in that 1 degree, maybe 1 or 2 observations per cell.
That's true.
Something like that. So there is a limitation about the in-situ data. Why do you think that this in-situ data limitation is, let's say, weaker than the satellite data limitations?
Because
you're criticizing the satellite.
That's right. No, but if you look at the stochastic properties, you know, so what happens in the in situ data is that, okay, can I write here, right? So if you have, let's say we have, you know, this is Glathida data. And, you know, if you have the thickness, let's say in the ith grade in time period t, you know, it's, let's say, A0 plus A1 plus some variable plus so on, and plus A, you know, maybe 10, let's say. This is Glathida thickness. And here it is thickness again. And this is the thickness in time period t minus 1. Now, if you look at the coefficient A10, you know, it is very reasonable. It may be something like A10 is approximately, you know, 0.25. Now, if instead of you are using remote sensing data and you have remote sensing data here, the lag value, you know, this A10, let's call it A10 star or remote sensing, let's say, this is approximately 1.0. The whole process has become non-stationary. So it's based on my statistical sort of experience of, you know, 40 years plus, it is not possible,
Of course,
to have such high degree of correlation between these variables unless the remote sensing data processing process was such that it actually induced these correlations. Go ahead.
This comes from the result of the analysis, not from the process. I mean, actually, you're criticizing the remote sensing data because of the trend that it appears in the end, and not necessarily because of the errors that are induced inside. So
The problem is, I mean, I've got
the problem is in the processing of the data that creates this problem that reveals itself in the final analysis.
This is the problem. I mean, you know, you're absolutely right. I've got just so much data. So, for example, you know, what they did was in the remote sensing data, if you go towards the North Pole, you know, in certain regions, they're actually using temperatures to predict ice thickness because the satellites are not really capturing the remote sensing. Now, I'm not criticizing the remote sensing thing. What I'm criticizing is that people like this Huguenot and so on, they never bother to check the stochastic properties of their data set. if they did, then, I've got one from in situ, it tells me, the lag dependent variable is 0.2, 0.25 or whatever, and one where everything is converging to one. I mean, that's really not feasible. So, I mean, I agree with you because I wrote some algorithms too. Sometimes, for example, I've got, 256 quarterly observations. And obviously I can't, the whole University of Maryland system once collapsed because my student made an error and they took away because we've got terabytes and terabytes of data set it actually generates. But, they're very proud when you present these results to climate scientists. They say, oh, you've got petabytes of data we've got. But the point I'm trying to make is you can't use them unless you put the numbers for every year in an ASCII format so I can access them and or anybody can access them and see what happens over time. But if you can't, then we're not sure what is happening to the climate. I mean, everybody is saying glaciers are disappearing, but they're not disappearing at that rate. I mean,
Yeah. Okay, it takes econometricians to understand what you're saying, but it needs to be communicated,
That's
and it's so obvious to somebody who's been dealing with data in econometric context to
Right.
understand the process, the data generation process. This is an impossible one.
I'm hoping to get your help in getting.
Yeah.
points
I
across.
got what you're saying. I got what you're saying. Okay.
Sorry, there's one more question.
Yeah, please.
Thank you very much.
Yes.
Here you will put the machine learning techniques or evolution neural networks to one of these processes or to pre-process the data, in order to clean the data.
No, I've just, sometimes what happens is that if you look really at the North Pole, the temperatures do not change for the whole year. And that's really not possible. And so it must be, so what I did was I wrote some algorithms that if the temperatures, I had a series of 256, now I don't know why I've got that number, but I think it was 20 years, 4 time periods, so it's 80. But anyway, if the temperatures series was the same, then my algorithm would actually drop that observation. But no, I'm not. In fact, I mean, part of these things are due to the mechanical sort of adjusting of data. And so I've been trying to avoid that. So I don't want to create any further problems. So I'm basically looking at the data as they're given to me. I'm not doing anything at all to process them further, except taking some sample means to reduce the variation over time.